With this in the background, let us go and look at a problem involving designing a column. The height is h, the diameter is d, and the column is supposed to support a compressive load F. You want to have the minimum weight to, to address two failure constraints, one by crushing and the other one by buckling. And you want to look at minimizing costs for each constraint and specifically the material cost. So for doing this, we need to derive two performance equations for the material cost. One for the crushing constraint and one for the buckling constraint. Once we have that, then we'll get two material indices based on the two performance equations. The two material indices are related to each other based on the coupling equation. That's something that we saw in the previous week. Let's put these things into perspective for this specific case study in this design exercise. So what's the function? What are the constraints? What's the objective? What are the free variables? Right? So the function is a column. The constraints are twofold. Right? It should not fail by compression. It should not fail by buckling. And the height is specified. And let's say the compressive load F is also specified. The objective is to minimize the material cost to satisfy each of those constraints. You're free to vary the diameter, and so that's a free variable. It's not specified. And the material is not specified either, so you have a choice of materials. So first thing we have to do is to write an expression for the material cost, which is mass times the cost per unit mass. Mass being volume for the geometry for the cylinder times the density based on the material. Then for the compressive crushing strength, you have an equation, and then for the Euler's buckling strength, you have another constraint. If you use that to substitute and eliminate the free variable d, you can derive the cost of the column. And the cost equation, which would depend upon the load, right? The higher the load, the more expensive the column. The bigger the column, in this case, the height, the more expensive the column. And then depending upon the material index, right? The higher the material index, the lower the cost. Right? Those are some things that you have to look at. So let's see how we can compose the equations that define cost for columns based on each constraint. So cost is the mass times the cost index, and mass is the volume of the cylinder times the density, and then you'll get mass times cost, right? Cost per unit. This Cm is the cost per unit mass. So the crushing constraint, you can look up Appendix B5 in your 4th edition of the Ashby book, and you will look at the fact that 4F by pi d square should be less than or equal to sigma c, the compressive strength. You can get the Euler's buckling constraint from Appendix B2 and B5, where from B5 you'll get F as pi square times EI by h square, and B2 will give you what the moment of inertia is. For the cylinder, it's pi d to the power 4 divided by 64. D is the diameter, h is the height, rho is the density, Cm is the cost per unit mass, E is the Young's modulus, sigma c is the compressive strength, I is the moment of inertia. Right? So far so good. So let's take that equation for cost that we looked at based on the volume, the density, and the cost per unit mass, and apply it to the first performance constraint based on crushing. And so the failure force should be less than or equal to pi d squared divided by 4 times sigma c. In the second case, the buckling constraint, the failure strength F should be less than or equal to pi squared times EI by h squared. If you substitute that for the moment of inertia, you'll get pi cubed d to the power 4e by 64 times h squared. Give this a try. So our job is to eliminate d square from each of these equations and substitute over here in order to compute a cost. In the first case, that is F times H times this combination of material properties. And so Cm rho by sigma c will be your one index, in this case a cost index, right, as a performance index. In the second case, based on the second constraint, you will basically have C2, if you simplify this expression over here as this whole equation, where the cost index or the performance index based on just materials is Cm rho divided by the square root of the modulus. So somewhat different, these two. Of course, if you're minimizing based on one constraint alone, all you have to do to minimize the cost is to maximize this sigma c by Cm rho. Let us see how we go about doing this. So we have gone ahead and derived the two material indices, and we have composed the two performance equations. We would like to get to the point where if these two indices were the same, okay, Cm rho by sigma c and c, for that to happen, for the costs of these two to be based on the two constraints to be the same, if you can set C1 equal to C2, you will get an equation that begins to relate when are these two costs the same.